Good afternoon to everybody. I'm Georgakakis from the National Observatory of Athens, and what I will be discussing today is a new model for the ensemble variability of active galactic nuclei in order to infer information about physical properties of the population. And the one physical property or relation that I will be talking about mostly is the stellar mass black hole mass relation of AGN from variability studies. So just let me start by defining what I mean by flux variability or the variability of AGN. And this is what I mean by that are the stochastic variations of the intrinsic flux of AGN. And an example of such a variability is shown on the plot here on the lower left part of the slide, where you can see for a local AGN how the count rate on the vertical axis changes as a function of time on the horizontal axis. And you can see all those data points, the flux of the source at different time intervals, and you can see that they jump up and down in a rather erratic way. And this is exactly the variability I will be discussing in this presentation. Now, there are many ways to quantify this variability in the light curves of AGN. I will be using two methods in particular in this presentation. The first one is the power spectral density or power spectrum of AGN, PSD, which is shown here on the top right part of the slide. And what the power spectrum is essentially the Fourier transform of the light curve. So this plot here at the top right shows the amplitude of the Fourier frequency of the Fourier components on the vertical axis, and this is plotted as a function of the Fourier frequency on the horizontal axis. And the data points on this plot correspond to the light curve of the AGN shown here, the light curve of which is shown here. And you can see that the power spectrum kind of follows a double power law distribution with a slope of about -1 at very faint frequencies and -2 at high frequencies. It turns out that this kind of behavior, this functional form, is generic for many, if not all, AGN. Another way of quantifying the variability of AGN that I will be using in this presentation is called the normalized excess variance. The equation here is defining what that is. The details are not very important at the moment, but essentially what the normalized excess variance measures is the variance of the light curve, the intrinsic variance of the light curve once Poisson shot noise is accounted for. And a property of the normalized excess variance that I will be using is that it is related to the power spectrum via a simple integration in frequency as shown here in the last equation. So it turns out as well that the variability of AGN contains information or depends on the physical properties of the accreting system, such as black hole mass and Eddington ratio. And the black hole dependence is demonstrated in this plot here. You see the normalized excess variance on the vertical axis, where higher values of the excess variance mean more variable sources, lower values, less variable sources. And this is plotted as a function of black hole mass. All the data points here are a sample of Lockhart-Siffert galaxies. And you can see that there is a clear anti-correlation between those quantities. And this is a strong indication that the excess variance and therefore the power spectrum depend on black hole mass. There is also evidence for a dependence on Eddington ratio. So I will be using this relation later on for the modeling. Now, it is possible to inverse this argument and say that once we know about the variability properties of a particular AGN, then we can infer physical parameters like black hole mass and Eddington ratio, because those two are related. What I will be doing in this presentation is really extend this argument from individual objects to populations of AGN. So I will be arguing in the next few slides that if one studies the ensemble, the average excess variance of AGN population, then it is possible to constrain the physical properties of the population as a whole, and in particular, the black hole stellar mass relation. The kind of data that this approach is using is coming from extragalactic surveys with multi-epoch observations. And probably the prime example of such surveys, such extragalactic surveys, is the Chandra Deep Field South. This is a field, a patch of the sky that has been observed extensively and intensively by the Chandra telescope at X-ray wavelengths. And the total integration time on that field is about 7 megaseconds. Now, these 7 megaseconds have been spread out in a time scale of about 17 years, and therefore observations in these, the Chandra observations in this field provide light curves for individual sources over a period of 17 years. Now, the light curves of individual objects in that field contain limited information. The shot noise is important, and therefore individual light curves contain limited information. However, it is possible to average many light curves together, group them in large samples, and stack them in a way. And therefore, the information content of the group is increasing. And as I will show you later on, with the right modeling, it is possible to draw conclusions on the black hole distribution and the Eddington ratio distribution of the population. So this is an example of ensemble variability of AGN. And this is also the plot that I will be modeling in the next few slides. These are the observations I will be modeling. So what is shown in this plot is the ensemble excess variance on the vertical axis of AGN in the 7 megasecond Chandra Deep Field South. This is the field I was talking about previously. This is very well suited for this kind of analysis because it has multi-epoch observations. And then some variance of sources in this field is plotted as a function of X-ray luminosity of visual AGN. So you see in this plot two sets of data points. Focus first on the gray data points. Those are individual AGN in the Chandra Deep Field South. So those are ensemble excess variances, normalized excess variances of individual sources in that field. And you can see that the error bars of these data points can be quite large. And therefore, there is a lot of scatter in the gray points. And this is partly related, of course, to the larger uncertainties that individual light curves of the light curves of individual AGN in that field have. However, it is possible to group those data points in luminosity and estimate averages or the ensemble in X-ray luminosity. And this is shown with the crosses, the black crosses. And you can see then that a clear trend emerges in the sense that the ensemble excess variance is anti-correlated with X-ray luminosity. More luminous AGN appear to be less variable than less luminous ones. And this is the plot that I will be modeling. And this anti-correlation contains information about the black hole mass distribution of the population, as well as that of the Eddington ratio distribution. So how can I model this plot? This slide is a summary of the modeling approach. The three boxes that are shown here in black are the three components of the modeling. And the starting point is really to simulate AGN and their host galaxies in a cosmological volume. Now, I'm not going to go into details of how this is exactly done. The important point is that this simulated sample of AGN and their host galaxies is based entirely on observational quantities and relations. And in particular, the relevant quantity here is the specific accretion rate of AGN. This is shown in this slide here, in this panel here, and it is possible to use this observationally derived quantity to populate galaxies with AGN, and therefore end up with mock AGN samples. And these mock AGN samples include a catalog of simulated AGN, and each of these AGN is identified or is assigned a luminosity, a redshift, and the stellar mass of its host galaxy. Now, once this component is in place, the next step is to make some assumptions about the black hole mass of individual AGN and galaxies. And since stellar mass is available in the mock catalog, it is possible to use a parameterization of the black hole and stellar mass relation, like, for example, shown here. And having this parameterization, having this relation, one can associate mock galaxies and AGN with a black hole mass. And once you have a black hole mass for an AGN, there is also information about the Eddington ratio, because the previous step already assigns mock AGN with AGN luminosities. And those two last components, black hole mass and Eddington ratio, are very important, because we know that the power spectrum of AGN depends on those properties. So if you know about those two properties, it is possible to predict the variability of AGN given a model parameterization for the power spectrum. So a possible parameterization of the power spectrum is shown here. And with this parameterization, you can associate individual mock AGN with a power spectrum, and therefore, through this simple integration, estimate excess variances for individual AGN. And then if you average together in luminosity bins, it is possible to estimate at the model space the ensemble excess variance of the population as a function of X-ray luminosity and compare it with observations. And this type of comparison is shown in this plot here. The data points are the measurements of the ensemble excess variance of the Chandra Deep Field South. This is the plot I showed earlier, and the pink shaded region is the modeling result. Now, what I will be doing in this in the next slide is to set up a Bayesian inference model. I will parameterize the black hole stellar mass relation, and the free parameters of this modeling are alpha and beta. And by trying to model the observation, to reproduce, to fit the observations on the ensemble excess variance versus luminosity, I will try to infer the kind of parameters that are consistent with those observations. Now,
3 minutes.
Okay, thank you. So it's not only in this modeling, it's not only the black hole stellar mass relation that is parameterized, it's also the power spectrum. And this is the modeling I assume power spectrum. You can see here that is a broken power law with three parameters, alpha, amplitude, and break frequency. And those two free parameters, the amplitude and the break frequency, are actually related in the modeling to the physical properties of the AGN, the Eddington ratio, the black hole mass, via these relations. Now, I didn't come up with those relations from first principles. These are observationally motivated parameterizations. Local studies of local Seyfarths suggest that the power spectrum of AGN can be represented by these relations. All right, so those are observationally motivated relations. So I can throw this modeling into the Bayesian inference machinery and then try to fit the observations, right, of the ensemble variability. And these are the results of this fitting. Now, there are consequences from this Bayesian fitting analysis. There are consequences both on the black hole stellar mass stellar mass relation, as well as on the power spectrum of AGN. In this presentation, I will only talk about the black hole stellar mass relation. So just a reminder that this is how the modeling, this is how this relation was modeled. This is the fit to the data, the ensemble excess variance versus X-ray luminosity. The pink shaded region shows how the model fits the observations, which are the data points. And the plot here at the top right shows what are the implications of this modeling on the black hole mass stellar mass relation. And the pink shaded region is are again the constraints from the model. The width of the pink shaded region corresponds to the 68th confidence level. This is approximately 1 sigma uncertainties around the median. And you should compare that pink shaded region with two competing models for the black hole mass stellar mass relation in the local universe. And the first of those models is shown here with a red dashed line. The second model has a lower normalization and is shown with a solid green line. And you can see that the ensemble variability results are more consistent or favor the red dashed line, which is based on dynamical black hole masses. So this is the main result of this analysis. And I'll just conclude here by saying that there is potential to constrain the black hole mass stellar mass relation using the ensemble variability of AGN populations. And I have presented in this presentation a model that can help interpret the data in the context of physical relations like this one. Now, the main limitation of the result I presented is the small sample size. The data points that I presented in this figure that are coming from the 7 megasecond Chandra deep field south are essentially coming estimated from a total of 200 sources in that field. And this is too small. However, there is hope for the future because many of you may be aware of the eROSITA All Sky Survey, the eROSITA telescope that is out there taking observations at the moment. Earlier last week, there was the first data release of the eROSITA telescope was done. And what the eROSITA will be doing is that it will be scanning the entire sky for over a period of 4 years. And the scanning pattern of the telescope is set in such a way that it provides an all-sky survey every 6 months. And therefore, the eROSITA All-Sky Survey, after 4 years of operations, we are halfway through that at the moment, will provide light curves for millions of AGN with a cadence of about 6 months. And these numbers are sufficient to start thinking about estimating the ensemble variance of that sample as a function of observables like X-ray luminosity, stellar mass of the host galaxy, and redshift. And therefore, with eROSITA, there is the potential to constrain the black hole mass stellar mass relation as a function of redshift. So that's all I had to say. Thank you for your attention.
Thank you very much, Adonis. Any questions? We have time for 1 or 2. Vasilis, wait a second. You should be able to unmute now.
Thank you. Thank you, Adonis. Very interesting talk and very interesting problem that you are trying to address, actually. One thing I didn't quite understand, you mentioned it earlier on, right? You said that you would be doing some effectively stacking on light curves, right? But isn't this, you know, since it's a time series, right? I have hard time kind of like understanding how, for example, difference in the time period between the variability of the various sources, why this will not actually affect your result by definition, right? It's not as if this, yeah, it's not the same as if we get, you know, bright galaxies and faint galaxies, right? Where a specific population may affect us. That's why right. I cannot understand it conceptually.
I guess you are asking that, you are saying that you know, there are different time scales on the light curves depending on the redshift
right,
of the source.
right,
yeah.
right.
So yes, I mean, this is true. So essentially you have here your light curves, your data point, the gray data points is the ensemble excess variance of different AGN at the rest frame of the source, right? Well, this is estimated at the rest frame of the source, and different sources correspond to different redshifts. So this 17 years time span that I write here correspond to different rest frame durations. And this is not corrected for, right? So I'm simply stacking up or averaging normalized excess variances of individual data or the individual sources, the gray data points. However, this dependence is taken into account in the modeling. So the modeling, in the model, you have a population of AGN at different redshifts, and you assign to them variabilities. And therefore, you do the same thing as in the observation. Now, ideally, you would like to do that in redshift intervals. So you would like to split your sample in redshift intervals. And therefore, in this case, the 17-year time scale would roughly correspond to the same rest frame time interval as well. However, the Chandra-Deep South data are not, you know, the sample is not large enough to do that. So this is where you need like a larger sample to start splitting in redshift space as well, and properly, or not properly, but you know, get more information, right, out of your data. This is what it's all about. The information is somehow stacked up in the case of Chandra-Deep Field South, but you can, if you have a larger sample, you can have this additional source of information.
Yeah. Thank you.
The modeling.
Any other questions? I would just a follow up on Vasily's question and also a follow up on your last future prospect. Is it with more data, let's say, will you be able to actually beat this intrinsic scatter of your correlation of your fit, or is this a scatter that you can beat with more data, or is a real scatter that
this over here
from the previous? Yes, that's scatter.
Right. Yeah, that's a good question. I don't think I have a good answer to that, right? Well, so, I mean, right. So if you want to constrain the black hole mass stellar mass relation, right, what you should really be doing is estimating the excess variance, not as a function of luminosity, but as a proxy to black hole mass. So you would like to do that as a function of stellar mass, for example, if that's your observable. Now, the excess variance, or the power spectrum of AGN, we believe, or there is evidence suggesting that also depends on Eddington ratio. So you want to disentangle those two, black hole mass dependence and luminosity dependence, Eddington ratio dependence. Now, a proxy of your Eddington ratio is the X-ray luminosity, right? So by plotting here in this figure excess variance only as a function of X-ray luminosity, you essentially stack up all the stellar masses or black hole masses, if stellar mass is a proxy to black hole mass, together. So having a large sample where you can actually disentangle those two, you know, and this is where this point goes, right? Yeah. Estimate ensemble variance as a function of those three parameters, then this will definitely decrease a little bit of the scatter. Now, the question, I mean, E Rosita is photon limited, right? It's not background limited, it's photon limited. Whether the light curves will have the sufficient statistics for the variability to be detected, the intrinsic variability to be detected above the Poisson noise. I mean, I think this needs a little bit of exploration, really.
Thank you. Very interesting. Yes. Yeah.